In this video, we're going to cover section 6.2, which is going to be on the sum and difference identities. And these are the main four right here. We will have two for tangent, but these are going to be the ones we'll use the most out of the sum and difference identities. I will post a video right after this one going over the proof for this specific sum formula for sine. The remaining three formulas can be found in a similar way. But is what I want to do first is just cover here how we can use these formulas or how to use them. Okay. And so here's one example. Okay. So for one, we're going to use these to some extent to find sine, cosine, and tangent of angles that maybe aren't the ones that we're used to seeing on the unit circle. Okay. But they still will need to be either a sum or a difference of two angles that come from the unit circle. So for instance, like 15 degrees here, we have actually a few options. But one option here is if we were to think about, let me go ahead and write it over here. 45 degrees is a very common angle that we use, right? And so is 30. Okay. And well, it ends up, if you subtract those, you end up with that 15. Okay. So what I'm going to do is I'm going to rewrite my sine of 15 here. Again, note this is an angle. It's not one of the common angles that we're used to on the unit circle. So we're now going to rewrite it as sine of the difference of two angles that we're used to seeing on the unit circle. Okay. And this isn't helpful unless we have a sum or difference formula here, and we do. Okay, we have it right here. This is the one we're looking for. We have sine of a difference. So I'll write this as sine of my first angle, cosine of my second angle, minus cosine of my first angle, which is 45, and then sine of my second angle, which is 30. All right, and again, the reason that this is really helpful is I can go through and actually evaluate all four of these things here. Okay? For instance, sine of 45, well, that's just equal to the square root of 2 over 2. Cosine of 30, that's equal to the square root of 3 over 2. Okay. Cosine of 45 is root 2 over 2. And sine of 30 is 1/2. And the only other thing we could really do with this is we could get a common denominator and add these things together. Okay. We're not actually going to have to get a common denominator because they already have the same denominator. But let's do one step before we actually go ahead and subtract these two sets of fractions here. Okay. So let's multiply here. If we were to multiply these, this will give us the square root of 6 over 4. And then over here, this is going to give us the square root of 2 over 4. And then finally, I can now subtract these. So I get root 6 minus the square root of 2 all over 4. Okay. And again, this is kind of neat. So this allows us to evaluate now our trig functions at multiples of 15 degrees, something we, again, don't see on our common unit circle there. So let's try out this one. So similarly, I want to try to find two angles from my unit circle. Again, those multiples of pi over 6, pi over 3, pi over 4. I want to take two of those and add them or subtract them to get this 5 pi over 12. And sometimes it takes a little guess and check. You might not guess the right angle that you want right off the bat here. I have one in mind that we could try. So it might be actually helpful to know, what quadrant 5 pi over 12 lies in. Okay. Well, 5 over 12 is just short of 6 over 12. So this is just short of pi over 2. So this is in the first quadrant. Okay. So I'm really going to be thinking about maybe subtracting angles in quadrants 1 and or 2, okay, then to get this angle, depending on what ones I add or subtract. But maybe if we try maybe like pi over 3 minus pi over 6, that might be a good first try. Okay. Let's try that. See if we have any luck. Okay. We might have to adjust it, but it's okay. And I was going to do this by hand, but we most certainly could check these really quickly on the calculator. I think this is going to give me something too small, but I do want to emphasize that, at first it does take a little guess and check here. So yeah, this gave me something way too small. And of course, pi over 3 minus pi over 6 is going to give me pi over 6. Okay. Well, let's maybe try the other way around here. Let's maybe try pi over 6 plus pi over 3. Let's see what that gives us. Okay, so if we do 1/3 plus 1/6, we're getting 0.5 here. Okay, so that didn't seem to work out very well either. Okay, well maybe let's start messing around with maybe using like a quarter and a third. Let's maybe try something like that. Because right, we're used to seeing kind of angles are we used to seeing pi over 4s, pi over 6s, pi over 3s, and their multiples. So yeah, let's try an over 4. Okay. And let's maybe try to add a 6th to that. That's my guess. So yeah, that will get it done. So we're going to use pi over 4 plus pi over 6. And again, that gives us 5 pi over 12. Okay. So that's why this is going to work out for us. Okay. So now we need to figure out which one of those identities up there we need to use now that we know this. Okay. But maybe I could just start off by writing, we have cosine of pi over 4 plus pi over 6. There we go. All right, so let's go up. So if we're looking for a sum, we want to use this very top formula. And when I say sum, I mean cosine of the sum of two angles. So I'm going to leave this right here, but I'm going to eventually erase it. But this is the formula that we're going to use. Okay. And it says to do cosine of the first angle, cosine of the second angle, and then subtract sine of the first angle, and then sine of the second angle. So this is going to work out a lot like that last one here. Okay. Let me see if I can get rid of this thing here real quick. There we go. Okay. So we'll go through and we'll evaluate all these. Cosine of pi over 4, that's root 2 over 2. Cosine of pi over 6, that's root 3 over 2. Sine of pi over 4, that's root 2 over 2. And sine of pi over 6, that's 1/2. Okay. So yeah, this looks a lot like the last one. If I were to multiply these together here, I'm going to get root 6 over 4. And multiplying these two together here, I'll get root 2 over 4. So yeah, we actually, I think, got the exact same thing there. Yeah. Root 6 minus root 2 all over 4. All right. But you can see why maybe people have avoided putting multiples of, say, 15 degrees or these angles that, have a pi over 12. You can see maybe why they didn't put them on the unit circle for the angles that were expected to memorize the x and y values. And this is because we end up with things that look like this. They're not going to fit very well on that unit circle. Okay. All right. So this one's going the other direction. Okay. So now we have things being plugged into our cosine and sine that we can evaluate still. But it might be helpful to instead, so is what I want us to do is go up top and look for something that looks like this. Okay. Again, we're going to use these in the other direction. So I'm looking for, cosine, cosine, and sine, sine, and they're being added together. So that sounds like the second one right here. I'm going to go ahead and highlight it, and we'll verify that it's the right one here in a second. All right. Yeah, this is exactly what we have. But the first thing we need to do is identify maybe what alpha and beta are. Okay. For instance, alpha is going to be that first angle, and beta is going to be the other angle, this one here. Let's go ahead and write that in. There we go. And then is what we can write here is cosine of alpha minus beta. So in other words, 5 pi over 12 minus pi over 12. I'm going to scoot this over so that it's a little more clear that the line I just wrote is equal to what we're trying to show. Okay. So let's keep going. So if we subtract these, we're going to get cosine of 4 pi over 12. Well, that's really just cosine of pi over 3. And cosine of pi over 3, well, that's just 1/2. So that's the last one of those that we're going to do here. The remaining ones are going to be verifying trig identities. All right. So we have this one to verify right here. Okay. And again, I want you to notice kind of the same thing with our previous identities that we were looking at, which is one side does look a little bit more complicated. Okay. But I also want us to note that on one side, we have identities we can apply, but the other side we don't. Okay. So what I'm getting at is the left-hand side here. Not only does it look more complicated, but this reminds me of the identities we just learned. So I'm going to pick that side to start with. Okay. And if we went up to look at the formula for cosine of alpha plus beta, it's this one. Why don't I just copy both of these, because we're going to wind up using both of them. There we go. There we go. So if I start writing out cosine of alpha plus beta, this should be cosine of alpha, and I'm going to leave out the parentheses just to make this a little bit quicker to write. Cosine alpha, cosine beta, minus sine alpha, sine beta. And then you can see the only difference between cosine of alpha plus beta and cosine of alpha minus beta is the sign here in the middle. So for our next set, the cosine of alpha minus beta, we're going to have plus cosine alpha, what is it? Cosine beta, plus sine alpha, sine beta. I said I was going to leave out those parentheses. Let me actually do that. There we go. Okay. So next, I need to get rid of these identities that I brought in from up above. Let me see if it'll let me do that. There we go. Okay. Now, you may notice there are some like terms here. For instance, I have two of these. And then these two here cancel. And so I'm actually already done verifying this identity. I started with the left-hand side. All I had to do was apply our sum and difference identities, combine like terms, and then we've wound up with the right-hand side. All right, let's give another one of these a try. Here we go. So this time, I think the more complicated side looks like this. But I also am noticing this sign of alpha plus beta. So this looks again like one of the identities we just learned. So this might be a reasonable place to start. I'm going to do just that. I'm going to start on the left. There we go. And actually, I'm going to write it on the next line what I'm going to do. But yeah, we're going to come up here and we'll get the identity we're looking for here again. And it was sine of alpha plus beta, I believe. So that's this third one. Let's go bring this down here. So sine of alpha plus beta, I can rewrite here is sine of alpha cosine of beta plus cosine of alpha sine of beta. And then I'm going to leave the denominator just as it is, cosine alpha cosine beta. And then let me get rid of our identity. There we go. So still note, I still have one thing, but I want to turn it into two. Well, I could split up the numerator here. Let me show you what I mean. It's like the reverse of adding fractions. We're going to break it back apart. Okay, there it is. So what I want you to note is for both of those fractions that I've written down, we have the same denominator. So if we were to add these two fractions together, we'd wind up back at our previous step. So this makes sense. So let's go ahead and see what simplification we can do. I think some things are going to cancel here. Let's see. So it looks like we're losing our cosine alphas over here, and then our cosine betas over here. And then sine alpha over cosine alpha, that's tangent alpha. And sine beta over cosine beta, that's tangent of beta, which is the right-hand side of that identity that we started with. So we verified this identity. Right. So I have one more here for us before we look at the next set. Okay. So once again, I see on that left-hand side two identities that we just learned. So I think those might be a good place to start. I'm going to write down my left-hand side. And then there's two identities we need. We need the two sum and difference identities for cosine. So I'm just copying those over. Bring them down. Go. So let's start off by applying these. I'm going to start off by just writing our work here to the right, but I'll move it below here in a minute. Okay. So maybe that looks about long enough. So on the top one here, I want to use the top formula, so that works out conveniently. I have cosine alpha, cosine beta, minus sine of alpha, sine of beta. And in the denominator here, I'm going to use the bottom formula. So we have cosine alpha, cosine beta, plus sine alpha, sine beta. There we go. All right, now let's make a note here. We want to eventually get to this. Okay. We want to somehow get some tangents in here. Well, there is a trick to this. Okay. I know that I want to wind up with a 1 here and here. Okay. That would be this spot and this spot. Okay. And notice that those are the exact same thing. They're both cosine alpha, cosine beta. So if I were to divide both of those by cosine alpha, cosine beta, they would turn into 1s. Okay. Now, I want to be careful about this. I need to make sure to actually divide the entire numerator and entire denominator by cosine alpha, cosine beta. And so we can do just that. Okay. And I want to note that when we do this, because we're dividing both the top and the bottom by the same thing, we're really not changing what it's equal to. Okay. It essentially is what I'm doing is something like this. Actually, let me pick a better set of numbers here. 24 and 6, right? You could divide the top here, say, by, I'm not going to use 6, although I know I could here, but you could divide these both by, say, 2. And if you did that, you'd get this. Okay. And these are equivalent to the same thing. Okay? And this is because, again, you've done the same thing to the numerator as you did to the denominator. Okay? So let's keep going. So I am going to take those two pieces and do just like I said. I'm going to divide both the numerator and denominator by this cosine alpha, cosine beta. So it's going to be very messy here for a second, but then it will simplify very nicely. Okay. So that's just the numerator. And then our denominator here, again, we want to divide everything here by also cosine alpha, cosine beta. And this should be addition here. There we go. All right. So you can see that those first two terms do become 1, just as we had hoped. And by first two terms, I mean the first term in the numerator and the first term in the denominator. But let's see what happens with these two things over here. Okay. I want you to notice I'm going to use a different color. Let me use maybe blue here. So sine alpha over cosine alpha, that would just be tangent of alpha. Okay. And we also end up with a sine alpha over cosine alpha down here. That's tangent alpha. And then the sine beta over cosine beta that we see in the numerator and denominator, those are both going to become tangent of beta. And we have officially verified that identity. Okay. We've ended up with the right-hand side here. Right. So this brings us to our last two sum and difference formulas, and specifically they're the ones for tangent here. Okay. So this right here, you could actually come up with both of these formulas For instance, for tangent of alpha plus beta, you can get this identity by using sine of alpha plus beta divided by cosine of alpha plus beta. Now, you might have to do a little extra simplification, but you can get there just using this. Okay. In fact, your work will wind up looking a lot like what we've done up here in this previous problem, if you were to try it. And I do think if you have time, it's worth putting in the effort to see if you can show these, because I think you can. All right, so now we're going to do two more types of questions. We're going to do one more identity, and then we'll look at this new type of question down here. All right, so notice that we have a sum inside of tangent here. Okay, so that should look a lot like this formula right here, which I'll copy and bring down here for us. And so do note, since I'm already bringing up this formula, you can probably guess I'm going to start off with that left-hand side. So I have my tangent of theta plus pi over 4. And if we use this formula, it should be tangent of the first angle, which is theta, plus tangent of the second angle, which is pi over 4. There we go. And then in the denominator, we should have 1 minus tangent of the first angle again. And then tangent of that second angle, which is pi over 4. There we go. All right, and so I need to copy this for just 1 second so that I can get rid of the identity and get it out of our way. There we go. Now, here's the thing. While tangent of theta, we might need an identity to maybe rewrite that and make it look like, say, a sine or a cosine. We don't need to do that with tangent of pi over 4. Tangent of pi over 4 is actually equal to 1. So we could rewrite this thing here as tangent of theta plus 1. And it's 1 because, right, sine and cosine at pi over 4 are both the square root of 2 over 2. And so if you do root 2 over 2 divided by root 2 over 2, you get 1. Okay, so we've ended up with this. Okay. And we somehow need to get to sines and cosines. Okay. So there's multiple ways we can get there. But one is we could just begin by rewriting our tangent as sine over cosine. Okay. Let's go ahead and do that. And so I ran out of room here, so I'm going to start us a new column here. Let's say equals here. Okay. So again, notice there are 2 spots. Actually, let's focus in on the denominator. Okay. I want a cosine right here. Okay. And note, I currently have a 1 there. So why don't I just try and see if it helps? And I'll try and multiply the numerator and denominator by cosine theta. So if we do that, this actually does simplify very nice. Let's see what we get. So if you were to take sine theta over cosine theta and multiply it by cosine theta, you just get sine theta because the cosines cancel. Okay. Similarly, if I do cosine theta times 1, I'll just get a plus cosine theta. And then in the denominator, cosine theta times 1, well, it's cosine theta, just like we intended it to be. And then this last set here, cosine theta times sine theta over cosine theta, is just going to be sine theta. And so we have ended up with that right-hand side. We verified this trig identity. So here's our last one. Okay. So this says to find the exact value of cosine of alpha plus beta under the given conditions. And we've been given two angles. And we've been told what quadrant they lie in. And we've been told some information about a trig function and what it's equal to at those two angles. Okay. So again, alpha here is in quadrant 4. So I'm just going to sketch quadrant 4 here. Similarly, for beta, which is going to be in quadrant 3, I'm going to make a sketch of quadrant 3. There we go. And then I'm going to put an angle in each one of these quadrants. So here's my quadrant 4 angle. Okay. And similarly, here's my quadrant 3 angle. Okay. Now, I don't know how many times or in what direction the angle alpha or beta are rotating. Okay. But is what we do know is where they land. Okay. And one lands in quadrant 4, one lands in quadrant 3. Okay. So the best I can say is, well, that this is my reference angle for alpha, and this is my reference angle for beta. Okay. But is what that allows us to do is make a triangle. Okay. And maybe I'll do that over here too. Okay. And we know that cosine, right, is adjacent over hypotenuse, okay, while sine is opposite. Let's see. Yeah, sine is opposite over hypotenuse. Okay. And then we could use our Pythagorean theorem to find the missing sides here. Okay. So for instance, this side here should be the square root of 3, because you'd get 2 squared minus 1 squared, and then you'd need to square root that. Similarly over here, I'd get 3 squared minus 1 squared, and then need to square root that, and so that'll be the square root of 8. Okay. And then, now, this is the, it may not be clear where we're going with this. All I've done so far is I've made a sketch of our two angles, okay? Well, we do have a trig identity that involves cosine of alpha plus beta. And let's see if that's going to be able to help us somehow. We'll go up and copy it too. Cosine of alpha plus beta. You might remember it by now, but I'm going to copy it. Here we go. And in fact, you know what? I'll just put it right here. Okay? And we'll go through and we'll start trying to calculate these things. Okay? So cosine of alpha. So is what I'm going to do is I'm going to look at our picture for alpha. Okay? And actually, I don't even need to do that. I already know cosine of alpha is 1/2. That was one of our givens. Okay. Cosine of beta, though, is not one of our givens. So let's go over to the beta picture here. And cosine of beta, okay, note what quadrant we're in. We're in quadrant 3, so cosine should be negative. Okay. And cosine is adjacent over hypotenuse, so that's going to be the square root of 8 over 3. Square root of 8 over 3. Now we want to find sine of alpha, which was not given to us, but we have a picture for it. And so sine is opposite over hypotenuse. Okay. So if we do opposite over hypotenuse, we get root 3 over 2 here. And then sine of, oh, and I should be careful here. I wasn't as careful as I should have been. So I do get root 3 over 2 here, but in this quadrant, sine is negative. So I need to put in my extra negative there. And then lastly, sine of beta, which we're given, was minus 1/3. So let's see what happens when we go ahead and multiply our two sets of fractions here. So it looks like I'm going to get a minus the square root of 8 divided by 6. And then I have a triple negative here. So it'll be minus the square root of 3 over 6. And if we want to, we can rewrite that as one fraction. We can write this as minus the square root of 8 minus root 3, and then all over 6. So this was nice. We didn't even have to get a common denominator. It was already there. There we go. Now, you could leave this like this if you want to. If you really wanted to, you could simplify the radical. The square root of 8 is 2 root 2. You could write this like this, but I'm perfectly fine with either one of these. And if you have kind of forgotten how to maybe simplify radicals like that, the idea is that you can rewrite maybe that 8 as a perfect square in another number, as a product, I should say, of a perfect square in another number. And then if you do that, when you take the square root of a product, you can just take the square root of each piece separately and then multiply. And well, the square root of 4 is 2. And the square root of 2, you can't simplify any further. And so that's how we ended up with this thing over here. All right, and so that wraps up 7.2 here. Okay, so we only have one more section of identities, and that's going to be 7.3.